Hi, everyone. I'm Martin Maas. I'm a PhD student at UC Berkeley. And today I would like to tell you a little bit about our efforts to bring a Java virtual machine to RISC-V. So why do we need a JVM for RISC-V? There are essentially two reasons. The first one is the obvious one. There are a lot of Java applications that we'd like to run, including things like Hadoop and Apache Spark. But there's also another reason. We would like to use it for academic research. There's lots of interesting research questions we could answer on, for example, how to do hardware support for managed languages. And these are somewhat conflicting goals. To run Java application, we really just want to port a really high-performance production JVM, whereas for academic research, we want an easy-to-modify research VM. So the question that we had to ask ourselves was, which of these JVMs should we actually port? And the conclusion we came to is, we're just going to port both of them. So to run Java applications, we are porting the OpenJDK hotspot JVM, which is essentially the gold standard for Java. The lead on that project is Michael Knischek, who's in the audience. And so far, you can actually run hotspot with the 0 backend, which is correct but slow. And Michael is currently working on a JIT port for that as well. On the research side, I've spent the last little while to port the Jikes Research JVM, which to date runs real programs with the baseline non-optimizing compiler. And this is what I would like to talk about today. So I'd like to talk a little bit about the Jikes Research JVM, how it works. I'd then like to share some of the lessons that we learned during this port in the hope that it will be useful for other groups wanting to port language runtimes to RISC-V. And finally, I'd like to give a little bit of an outlook where we're going with this work and where we are right now. So what's the Jikes Research VM? It was actually developed quite a long time ago, 20 years ago at IBM. Since then, it has been maintained by a number of research groups, including at ANU and UT Austin. And it's essentially the standard JVM used in most research papers. It has been used in over 200 research papers, won the SIGPlan Software Award. And what sets it apart from JVMs like, say, Hotspot is that it's actually written in Java itself, which is also called a meta-circular VM. So wait, how does that work? How do you write a JVM in Java? How do you compile it? So essentially what it comes down to is Jikes RVM is just a Java application, which means you can run it in an existing JVM. And it has everything that you would expect from a runtime system. It has a garbage collector. It has a just-in-time compiler. But of course, these components actually have to perform low-level operations on memory that are not supported in a Java runtime system. So the way this works in Jikes is that it supports special low-level primitives, like, for example, pointers or object references, which from the view of the application are just regular Java classes. But when they're encountered by Jikes JIT compiler, they will actually be translated to the real operations on memory. And this actually gives you a way to compile Jikes. So in order to compile it, you run Jikes in an existing JVM. Then you use it to load itself, which means that the just-in-time compiler will compile it and store it in memory using these special classes. And you can basically just redirect those memory requests into a large byte array, which you then store to disk as an image. And then you can just take that image. You write a small bit of C code that loads that image into memory. And then you just jump into that code that was previously generated. And then you have a standalone running JVM without any hosting environment. And that can then just load a Java application and run it. So this, of course, means that in order for this all to work, you actually need a complete JIT port, because the JIT is going to be used to compile the JVM itself. So why go through all this hassle? Why not just write your JVM in C? The main reason is really that this allows you to write systems-level code in a type-safe high-level language at a much higher level of abstraction, which makes it very, very easy to modify, even if it's like very deep modifications to your JVM, which makes this perfect for research, which is the reason that this has been adopted in the research community so much. So what I would like to do now is to go through some of the lessons that we learned porting this, which I think will be applicable to a lot of other runtime systems as well. So when starting a port like porting a JVM, one of the first things you need to get running are all your dependencies, and JVMs actually have a lot of them. So something that helps with that is that a couple of years ago, we ported the Pokey Linux distribution generator, which with one command can actually build all these dependencies for you, put them into a disk image, compile the Linux kernel for you, compile the tools for you, so you have all of that ready and don't need to do any extra work cross-compiling dependency by dependency. So once you have that, the next step is to actually build the JVM. And what we found to be very useful is to early on write a script that basically automates this entire process. It builds the JVM, it puts the JVM into that image generated by Pokey, boots that image in QEMU, runs the JVM, pipes the result into a file, shuts down the machine, and gives you your output. Here are a couple of examples for those kind of scripts. It's a very short thing to set up, but it's very, very useful because it gives you a very fast feedback loop. So now that you can actually build the JVM, the next step is to start with the actual port. And as the previous talk already pointed out, there's a lot of stuff that you can automate using the RISC-V opcodes repository. For example, things like generating your assembler. This also avoids a lot of potential errors that you might make trying to type it manually from the manual. So I can highly recommend it. While writing assembler, it's also a good time to start thinking about what to do about assertions. One thing we learned is it's a really good idea to have assertions everywhere so that you fail as early as possible. For example, you want to test for things like, does the constant you're trying to put into an immediate field actually fit? And one challenge we had was that early on in the porting process, you actually don't have all the machinery in place to actually handle assertions properly. So what we did in those cases was just to create a load that goes to an invalid location and causes a seg fault, then register a seg fault handler and dump all the state that you might want. You could also use GDB for this. So this is a very good way to early on catch errors and actually find where those errors are happening and how to fix them. So as you go along, you'll actually need more deeper debug information. And specifically for a just-in-time compiler port, what you ideally want is a trace of all the bytecodes that you're executing, as well as the stack state at a given time and the RISC-V instructions that are being emitted for each of them. So the way we implemented this was to actually allow the just-in-time compiler to selectively emit special instructions, which are basically causing a seg fault, in this case, once again, a load to an invalid location, and then include with those instructions a couple of metadata, such as what is the bytecode I'm executing, how many RISC-V instructions are associated with it. So what this means is that once you drop into your seg fault handler, you can actually print this nice debug trace with all the different instructions, the current state of your stack, and that's a very, very good way to debug this kind of code. One trick here, which is very useful, is you actually don't need to write your own RISC-V disassembler. Instead, you can just print DASM followed by a hex representation of your instruction, and then pipe this through the Spike DASM program, which comes with the ISA simulator for RISC-V. And then basically, you just get a nice disassembled output, which is really, really helpful for debugging. So now that you have the debug infrastructure in place, the next step is really to start implementing the entire JIT. And it actually turns out in order to even get a Hello World program to run, you need to basically support all features of Java, or like 95% of features or so. So it is what's much better to actually do this incrementally than try to port the entire JIT and then basically try to get it to work. And to do this incrementally, the strategy that worked well for us was to first, of course, switch off all the optional features like GC or bias locking or running on multiple threads, but then also to really find the first point where Java bytecode is getting executed. Because if you're trying to load a program into the JVM, you'll likely crash somewhere in the runtime system before you even get there. So it actually turns out that then some unexpected locations sometimes. So for example, in Hotspot, the first place where bytecode gets executed is in the static initializer of java.lang.string. In Jikes, it's a bit easier. It's in a Java, it's a vm.boot function. So if you put all your testing there and then incrementally start implementing bytecodes, that's a good way to get your just-in-time compiler running and get further through the boot sequence. One thing to think about early is the calling convention. The reason for that is that you'll have many different types of stack frames intermixed on the stack. So Java oftentimes calls into C, and then C code calls into Java. And your stack essentially becomes this heterogeneous structure with many different types of stack frames. So what we found is actually using the RVG calling convention, which is what the C compiler uses as well. That worked really well for us because it allows you to keep pretty much the same calling convention across Java and C frames. And the final bit has to do with exception delivery. We found that this is something that's good to get running really, really early, because the JVM actually, in its data structures, has a lot of information about which lines of code a certain instruction belongs to, etc. And to access that, you need to be able to take a hardware exception like a seg fault and deliver that back up into Java code. So jumping from that seg fault handler back into Java code. But if you get that running, you can actually get a nice stack trace that really helps to debug. Another thing related to exceptions that's useful to look out for is that there are some exceptions that Java expects that are not automatically triggered by RISC-V. So for example, a divide by 0 should in Java cause an exception, whereas on RISC-V it's basically doesn't trigger an interrupt. So those are the kind of things where you basically just need a mechanism to manually trigger an exception. And once again, we just used a invalid load, which drops us into that same handler where we then figure out which exception we have to call. And then basically you go through all these steps, you implement everything, and eventually you can run real applications. But it turns out that even to run a simple Hello World program, as I said, you have to support basically 95% of the JVM. In that whole boot process, you load 93 classes. It uses almost all the Java bytecodes. You need to be able to do dynamic linking and class loading, which actually includes loading a jar file, which is a zip, and unzipping it and finding the classes and compiling them. Java to C. You support reflection. You support pretty much all kinds of exception delivery, multi-threading support, synchronization, etc. So all of this, and then you can finally run Hello World. So where are we with this? So it's running real application. It's also passing most of the tests at this point, 65 out of 68. So you're still fixing up a couple of errors. It's still not perfect. It still crashes every once in a while, but it does run real applications to completion. We are next trying to look at how to run this on actual hardware. And we're interested in taking this to the next step, porting the optimizing compiler as well, and also pulling in some of the updates that the group at ANU has done to bring Jikes to the latest version of OpenJDK and the OpenJDK class library. At the moment, it's limited to Java 6, which is a little bit out of date. Eventually, we're hoping to upstream this and to use this in our research. Specifically, the reason we're doing all of this is we think this is really a great way to do hardware-software co-design research with managed languages. So one of the things I'm personally interested in is how to support garbage collection in hardware. We had a paper about that. Come find me after the talk if you're interested in chatting about that. Yeah, to wrap this up, in conclusion, we run real programs. Some of them have still small bugs. So this is a ray tracer. It runs to completion. Turns out the colors are a little bit off, so there's something probably wrong with floating point rounding modes or something like that. But it does run real programs to completion, and we think that this will be basically ready to upstream next year. With that, I'd like to take questions. And one more point, if you would like to get involved in either of these Java ports, we can use help, so please find me after the talk. Thanks.